Hello, welcome back. Today we will focus on Kirchhoff's rules, essential tools in analyzing electrical circuits, especially when dealing with complex networks involving multiple loops and branches. These rules help us understand how currents and voltages distribute throughout a circuit, and they are fundamental to circuit analysis in both theoretical and practical applications. Kirchhoff's current rule, also known as the junction rule, says that the sum of currents entering a junction equals the sum of currents leaving that junction. Mathematically, this can be expressed as the sum of I in is equal to the sum of I out. A junction or node is a point where three or more conductors meet. This rule is based on the principle of charge conservation. Essentially, if current flows into a junction, the same amount of current must flow out, since charge cannot accumulate or be destroyed at the junction. This rule is particularly useful when analyzing nodes in a complex circuit where multiple currents meet. It helps to write down equations that describe how current is distributed across different branches. Kirchhoff's voltage rule, also known as the loop rule, states that the sum of the electric potential differences, the voltage, around any closed loop or circuit is equal to zero. Mathematically, this can be expressed as the sum of V sub I is equal to zero. A loop is any closed path in a circuit, and this rule is derived from the principle of energy conservation. When you move around the loop, the total energy gained and lost must be zero because energy cannot be created or destroyed. This rule allows us to set up equations to find unknown values such as currents or voltages across components in a circuit. It is particularly valuable in situations where there are multiple loops and shared components between different branches. When faced with a complex circuit, it is often challenging to determine the currents and voltages by inspection alone. Here's a structured approach using Kirchhoff's rules. First step will be label the currents and directions. Assign a current to each branch of the circuit. It's crucial to choose a direction, even if you're not sure which way the current actually flows. If the direction is wrong, your calculated value for the current will simply be negative. Then apply Kirchhoff's current rule at junctions. So write equations for each junction where three or more branches meet. This helps ensure that the currents balance. Then apply Kirchhoff's voltage rule to closed loops. Identify independent loops within the circuit and write an equation for each loop. Make sure to consider the sign of each voltage drop and gain, depending on the direction of your loop relative to the components. And then finally, solve the system of equations. After setting up all the necessary equations, you will likely have a system of linear equations. Solve them for the unknown currents and voltages. For example, let's consider a circuit with a 12-volt battery, two resistors, 4 ohms and 6 ohms, and a resistor of 3 ohms that is part of a second loop. The current directions are chosen as I1 through R1, I2 through R2, and I3 through R3. Let's go step by step to solve this circuit. Keep in mind that for a resistor, the potential drops when moving in that direction of the current. For a battery, if you move from negative to positive terminal, the potential increases, and vice versa. Choosing current directions and voltage polarities consistently will help avoid errors. If your calculated current is negative, it just means the actual direction is opposite to what you initially assumed. Kirchhoff's rules are applicable beyond basic circuits. They are foundational for understanding AC circuits, alternate current circuits. It's analyzing where alternating current is involved, where impedances replace simple resistances, which we'll talk about that later. Power distribution, ensuring proper current and voltage regulation in complex electrical grids or in electronic devices, in designing and troubleshooting circuits in electronics, including transistors, diodes, and integrated circuits. So, Kirchhoff's rules are powerful because they allow us to break down complex problems into manageable equations. Then, by systematically applying these rules, we can analyze even the most intricate networks and predict how electrical quantities behave within them. May science be with you.